So now let's talk about another specialized binary probability distribution, which would be geometric distributions. Before we go into a geometric distribution, first we need to do is describe what a Bernoulli random variable is. So the probability mass function is the same thing that we've been looking at for a binary probability situation. But suppose we have a trial or an experiment whose outcome can be classified as either a success or a failure, and it's performed, right? And so if we let C equal 1, when the outcome is a success, and X equals 0, when the outcome is a failure, then the probability mass function of X is given by the equation that you see here. A random variable X is said to be a Bernoulli random variable after the Swiss mathematician James Bernoulli if its probability mass function is given by that expression. So suppose now that we have n independent trials, and each of which results in a success with a probability of p, and then a failure with a probability of 1 minus p. And if x represents the number of successes that occur in the n number of trials, then x is said to be what we call a binomial random variable with the parameters of np. The probability of x successes and n minus x failures for one arrangement of the order of results comes from our combination formula. Therefore, a Bernoulli random variable is just a binomial random variable with the parameters of 1, comma p. So we can take that random variable for one individual case, and then we can use that as part of our geometric distribution to describe the number of trials needed to observe a success. Each trial is going to be independent and identical, and it's going to be using our Bernoulli random variables. So this is very similar to what we saw with the binomial distribution, but the distinction here is that we're looking for the probability of finding the first success in a certain number of trials. So when we are calculating this, while a geometric distribution could easily be confused with a binomial probability distribution, instead of the expected value being np like we saw before, now our expected value is 1 over p. Our variance, remember for a binomial distribution, is going to be np times 1 minus p. But here, we're looking at our variance being 1 minus p over p squared. So our calculations are a little bit different because our emphasis is different, right? We're looking at when our successes are found.